Okay, hello, welcome to my channel. In this video, we want to find the antiderivative of this scary looking function right here. So we have the square of cosine of the inverse tangent of sine of the cotangent inverse of x. And we have to do that over the x variable. Oh, anyway, maybe you should pause this video and try this first. Let's do it together, right? That's why I'm here. Okay, so we see this. Well, we've done something similar to this in one of our previous videos, but it wasn't this complicated, or it wasn't this lengthy. But we are just going to be applying the same approach. It's just that we are going to apply it twice here, because this is 2 times more than the other in terms of the number of trigonometric functions we have. In the previous video we had just 2. Here we are having 4 of them, isn't it? Good. Oh, some of them are inverse tricks. Anyway, no problem. Now let's see what we have. Well, we have the sine of something. When we have sine of something, we usually think of sine of an angle, right? And in most cases, we use the notation theta to denote sine of that angle. So I'm going to call the domain of the sine function theta, right? Because it should be an angle. And of course, it's an angle, no doubt, but let's just see it the way we like to see it, right? So that means I'm going to say let theta be the domain of sine, which is the cotangent inverse of x. Good. So given that, we let theta to be the cotangent inverse of x, right? Okay, we are not going to differentiate this as always, but we are just going to do this substitution, which will help us to make this function a little bit easier for us to handle. Okay, so what are we going to do? Well, we are going to take the cotangent of both sides. So when we take the cotangent of the left hand side, we just have the cotangent of theta to be, well, when we take the cotangent of the cotangent inverse of x, in fact, it's just going to give us the identity x. That's what you get when you take the composition of 2 functions which are inverses of each other. Okay, very nice. So given this, cotangent of theta is said to be x. We can look at this on a rectangle triangle a little bit. We're going to see this. Let's call this the 90 degrees, right? Else this wouldn't be a rectangle triangle because I may not be perfect with my straight line. Okay, so let's look at the angle here is theta. This is the angle theta, right? So what we need is cotangent of theta. Here we have it to be x. Well, cotangent is said to be adjacent over opposite to the angle, adjacent over opposite. Tangent is opposite of adjacent, so cotangent will be adjacent over opposite, right? Good. That means we need to have something over something, adjacent over opposite. Here we are just having x. Where are we going to get the over something from? Well, you should notice that x is in fact the same thing as x over 1, right? So that means that the adjacent side is just x, and then the opposite side is just 1. This begs us to find out what the hypotenuse side will be. What the hypotenuse side is going to be the square root of the sum of the squares of the other 2 sides, right? So you are going to square 1, and then you are going to add it with the square of x. Good. So when we do that, we have the opposite side, the hypotenuse side anyway. Okay, so you notice that in a rectangle triangle, when we have all the sides, right, we can easily find out what sine of that angle will be or what the cosine of that angle will be. So here we need to find out what sine of theta will be because we've replaced the whole of this with theta. So that means this integral, let me clean this a little bit. Okay, so that means this integral will become the integral of cosine squared of the inverse tangent of sine of theta, sine theta, right? So sine theta from this rectangle triangle will be opposite over the hypotenuse. That's what we get from, that's what we get when we take sine of an angle in a rectangle triangle. So that will be 1 over, opposite is 1, then the hypotenuse side is just the square root of 1 plus x squared, right? Okay, that's nice. And then we can put the dx over here. Good. So now we have another thing. We are just going to do the same thing one more time. Because here we have cosine squared of something. So this should also be an angle, right? Notice we don't really talk about the inverse function because the inverse functions doesn't really have an angle, don't act on angles. Rather, they act on the results of the angle of their main functions. That's why they are inverse functions anyway. Their domain is the same thing as the range of their main functions. So the domain of tangent inverse is the range of tangent function. Okay, anyway, that's by the way. So let's see what we have. We want to call this, the whole of this, an angle. And I'm going to call it alpha, right? this is the kind of alpha I'm going to denote it with. That means we are saying that we should let alpha to be the inverse tangent of 1 over 1 plus the square root of x. 1 over the square root of 1 plus x squared, right? Okay, that tells us that if we take the tangent of both sides, right, we're going to have tangent of alpha, okay, to be, well, tangent of tangent inverse will just produce the original domain, which means we're going to have, or the original input, 1 over the square root of 1 plus x squared. Okay, nice. Similarly, we are going to look at this on a right angle triangle. Okay, let me call this x over 1. Let's see. Okay, so we have tangent of an angle is 1 over that, right? So if you look at this on a right angle triangle, where this is the angle alpha, and then of course this is the 90 degrees, tangent of alpha is 1 over that. Tangent is usually opposite over adjacent. So that means the opposite will be 1, and then the adjacent will be the square root of 1 plus x squared, right? Telling us that the hypotenuse side will be the square root of the sum of the squares of the other two sides. So we are going to square 1, we put it there, and then we add it with the square of this other side. So you notice this other side is under a square root. So when you square the square root, we're going to have the inside, which is just 1 plus x squared. And as you can see, this will be 2 plus x squared, right? Anyway, let's just leave it like that. We are still going to make use of it, that fact. So this will become the integral of, now we now have cosine squared of alpha, right? Because we've called the whole of this alpha. Looking at this right angle triangle, we can now find what sine or cosine or whatever trig function of this angle will be, right? So cosine squared of alpha is going to be the square of cosine alpha. So we are just going to have to square that when we are done finding out what cosine of alpha is. So cosine of alpha, from the right angle triangle, cosine of an angle is said to be adjacent of our hypotenuse, right? So that means we're going to have the square root of 1 plus x squared divided by this term, right? That will be the square root of 1 plus 1 is just 2 plus x squared. Oh, take note, from here to here, and you know what, they are all equal to each other. And the craziest thing is that we are still using the same variable x, and we are still doing that over the x variable. Isn't that very nice? Okay, very nice, isn't it? Now we now have to deal with this, right? So this in fact is a lot more easier than it looks. So we have the square of each of these square root term, and of course we are just going to take out the square root sign. We're going to have that, right? 2 plus x squared, and then we have the dx over here. So this now gives us an improper fraction. It is an improper fraction because the degree of the numerator is not less than the degree of the denominator. So to resolve it to a partial fraction, we will resolve it to a mixed fraction where we have a whole part and then the proper fraction part. Just the way we resolve improper fraction to mixed fractions, whole numbers and then the proper fraction part, right? Good. So let's see what we have. Well, you notice that this right here is just 1, right? Plus that. I'm going to do what we call addition of 0 in the numerator. By addition of 0, I'm going to just add 0 to the numerator such that the numerator doesn't change. You know, when you add 0 to something, you haven't actually changed that thing, right? So the version of 0 I'm going to add is going to be this. I'm going to add 1 to the numerator. Okay, and I'm going to subtract that 1 after adding it. So it's just like saying 1 minus 1 is just 0. The numerator stays the same. Good, but you notice what we're going to have when we do that. 1 plus 1 will give us 2, and then we add it with x squared. And in fact, let me split the fraction at the same time. So we're going to have 2 plus x squared at the bottom, and then we just have negative 1 hanging out. So we're going to have negative 1 over. We're going to maintain the same denominator. In fact, that is what it means to split fractions. The denominator stays the same, just that the numerator, you can split them, provided you're having an addition sign or a subtraction sign between these terms you are splitting. Okay, like in this case. So you see what we have in the first part of the fraction? We have this and that are the same, so we're just going to have 1, right? Okay, we're just going to have 1 here, 1, And in fact, I would like to split the integral at the same time, given that the integral of the difference of two functions is the difference of the integrals of those two functions. So that means we're going to have the difference of the integrals of those two functions. 1 over 2 plus x squared and then dx. And here is just the negative sign. Very nice. Okay, so let's see what we've got. Anyway, I'll clean this part of the board and then we are going to continue right here. Okay, so let's see. We have this to be the integral of 1 over the x variable, and of course that is just equal to x, right? Using the inverse power rule. And then we take that minus, well, the integral of this other function. If you like, I'll put the answer straight to you, and that is just 1 over the square root of 2, right? Times the inverse tangent of x over the square root of 2. And of course, when we are done integrating, we usually add an arbitrary constant. Okay, so how did we get this other part, right? Given this, we know a standard form or a standard structure. It is of this form. Look at this. When we have the integral of 1 over the square of a number, a non-zero number, right, plus the square of x, and we are to integrate this over the x variable, this in fact is equal to, you know, this 1 over a squared, right, plus x squared. So these two must be perfect squares. We have this to be 1 over a, then the inverse tangent of x over a, and of course we will add an arbitrary constant. You notice what we have here, this is just a 2, not a perfect square, not 2 squared, right? But you can change this to this form such that it will look like a perfect square, square root of 2 squared. So that means a here is square root of 2. If you square it, you just get the original function, the original term, and then 2x squared is still there. So the only difference was that 2, which we can get square root of 2 squared from 8. So that means a here will be replaced by the square root of 2, and that is the antiderivative of that function. Okay, very nice, isn't it? Thanks for watching, and please do well to subscribe to my channel, share it with your friends, and let me know what you think. All right.